Okay, let's just jump right into this explainer and demystify the absolute magic of fluid power. Think about it for a second. How on earth does a tiny input of force, like just pushing a button or pulling a little lever, end up crushing a solid steel car or lifting a massive commercial airliner right off the ground? It honestly feels like magic, right? But actually, it's just brilliant physics and engineering. Today, we're going to unpack exactly how the whole shebang works. Before we really get into the heavy physics, it is wild to think about just how ubiquitous hydraulic machines actually are. We honestly barely notice them, yet fluid power branches out into literally almost every sector. I'm talking everything from the massive agricultural harvesters that feed the world, all the way to incredibly precise instrumentation on space rockets. Oh, and even the intense sudden forces you feel on an amusement park roller coaster. It's everywhere.
So, to really grasp how this all comes together, we're going to build our understanding step by step. We'll start off with the dynamic range of fluids, then zoom right into the anatomy of a hydraulic system and the governing physics, specifically Pascal's law. After that, we'll look at force multiplication and its trade-offs, and finally, we'll tally up the fluid power ledger.
All right, let's kick things off with our first section, the dynamic range of fluids, going from a delicate touch all the way up to gigantic force.
What's truly wild to me is the sheer contrast in what these systems can do. The exact same underlying principles of engineered flow allow for vastly different applications. On one hand, you can have a robotic system delicately handling a payload of just a few grams, moving at creeping speeds of a fraction of a centimeter per minute. But then, using that exact same technology, you can power an excavator to generate a gigantic, earth-moving force of 36,000 tons. That is serious power. It really is the ultimate scalable technology.
Now, to truly get fluid power, we first have to draw a clear line and separate it from fluid transport. Fluid transport is, well, just about moving a volume of material from point A to point B. Actually, scratch that, it's just about delivery. Think of your municipal water pipes or a cross-country gas pipeline. Fluid power systems, though, they have a totally different objective. Their goal is to perform actual mechanical work. So instead of just delivering fluid, they use that pressurized fluid to act directly on a cylinder or a motor to, say, crush a car or lower an airplane's landing gear.
And within that world of fluid power, we basically have two paradigms, but we are specifically going to focus on hydrostatic systems. Hydrostatic systems rely on the mechanics of still fluids, using high fluid pressure trapped in a confined space to do the heavy lifting. This is totally different from hydrodynamic systems, like a dam turbine, which rely on the fast-moving kinetic energy of flowing water. We're focusing purely on the immense power of trapped, pressurized liquids.
Okay, so now that we've narrowed our focus to trapped, pressurized fluids, let's jump to Section 2, Anatomy of a Hydraulic System, and see how energy actually flows and transforms.
If we literally follow a single joule of energy through one of these systems, we see a beautifully clear transformation cycle. First, you have a prime mover, like an electric motor, which creates rotational mechanical energy. Second, a pump takes that mechanical energy and converts it into highly pressurized fluid energy. And finally, that pressurized fluid travels to an actuator, like a cylinder, which translates the fluid pressure right back into linear or rotary mechanical force to actually move a heavy load. It is essentially a real-time translator for energy.
And when you look at how the fluid routes through the system, it's this brilliant closed loop. The fluid just sits in a reservoir until an electric motor drives the pump, drawing the fluid in and pressurizing it. From there, that high-pressure fluid passes through regulators to keep things safe and filters to keep the fluid perfectly clean. Then comes the directional control valve, which acts kind of like the brain of the operation, routing the flow to push a double-acting cylinder at the very end of the line. That's exactly where fluid power is converted right back into physical lift or work.
To see how this all comes together in a real-world scenario, just think about a massive hydraulic car crusher. You can basically trace the engineered flow line straight from the motor and pump all the way up to an electrically controlled directional valve. By simply shifting that valve, the operator routes the high-pressure fluid to either the top or the bottom of a heavy-duty cylinder. That single action extends or retracts this massive crushing piston right onto the vehicle. It's incredibly elegant and honestly a little brutal all at once.
All right, with the physical anatomy all laid out, let's dive into our third section, the governing physics, or specifically Pascal's law. These are the absolute rules of the game.
So, the absolute foundational rule here is Pascal's law. Basically, it states that pressure applied to a confined fluid is transmitted undiminished in all directions. It acts uniformly on all surfaces at right angles.
The core equation you got to remember here is P equals F divided by A, or pressure equals force divided by area. Because liquids basically can't be compressed, any force you push into them is instantly distributed evenly throughout the entire container. Actually, it's the exact same reason why squeezing the bottom of a toothpaste tube forces paste out of the top. The pressure is transmitted everywhere.
And because of Pascal's law, we get our first really incredible application, seamless power transmission. If the area of an input cylinder is exactly equal to the area of an output cylinder, then the pressure results in an equal output force. So, a kilonewton input gives you a kilonewton output. What this means in practice is that we can route power from point A to point B around sharp corners through super tight spaces using simple, flexible hoses. It completely eliminates the need for complex, heavy, clunky mechanical gears. Now let's see how this builds into something even more incredible in our fourth section, force multiplication and trade-offs. This is basically the magic trick of engineering and the reality check that goes with it. Here is where the real magic happens. By simply making the output piston larger than the input piston, that uniform pressure is suddenly pushing against a larger surface area. If the output area is 10 times larger, your force is instantly amplified 10 times. No joke, this is exactly how just pressing your foot on a brake pedal can stop a 2-ton speeding car. But here comes the sleight of hand. The law of conservation of energy dictates you absolutely cannot get free power. To achieve that 10 times force multiplier on the output, you have to push the smaller input piston 10 times the distance. So the force is amplified for sure, but the distance is sacrificed.
This crucial trade-off really clicks when we look at the numbers in practice. Let's say you have a 25mm input cylinder, and you apply a tiny 125 newtons of force to it. Because the output cylinder is much larger, that pressure generates a massive 2,000 Newton output force. You've literally multiplied your strength. But remember that reality check. Pushing that small input piston a full 100 millimeters will only move your massive 2,000 Newton load a measly 6.25 millimeters. You have to pump that small cylinder many times to move the heavy load any significant distance at all.
So if we lose all that distance, why do engineers rely on this so much? Let's open up the fluid power ledger in this final section to weigh the advantages and limitations.
As with literally all engineering, it comes down to a balance. On the advantages side, we get immense multiplication of forces and an exceptionally low weight-to-power ratio. Plus, because hydraulic systems don't rely on electricity right at the point of work, they're spark-free, making them incredibly safe for explosive environments. But on the limitation side, we really have to take the risks seriously. We're dealing with extreme high-pressure hazards here, where a severed line can be genuinely devastating. These systems are also super susceptible to dirt, requiring strict, constant filtration, and they carry the severe environmental and slip hazards of messy oil leaks.
Ultimately, fluid power is just a masterclass in leveraging the strict laws of physics to our advantage. The next time you see a massive crane towering up in the sky, or a robotic arm delicately assembling a tiny microchip, remember the simple, elegant physics of confined liquids doing all the heavy lifting behind the scenes. It really makes you wonder, doesn't it? What impossible machines will engineered flow help us build next? Thanks for joining me on this explainer, and keep learning.